It is hard, and that's, um, well, I'm just being honest. I do worry that this is the first time I've run this summer class, and the summer class is definitely not the same as the semester class. The semester class is much more rigorous, is what I would call it. Uh, they take quizzes every week that are really difficult, that require a lot of prep, that is impossible to do in this format because there's not time to digest the lab, study for the quiz, and then take a quiz. It's just not possible. The Cody coursework is replacing it a little bit, but I don't see that many people like figuring it out, I would say, all the way. And the Cody coursework things that I'm having you, I'm giving you sections or parts from different quizzes I've done, but I do this thing where I do to get to, if you get to this part, you get a C. If you get to this part, you get a B, and to get to this part, you get an A. And your Cody coursework is just getting to the C for every quiz that I've written. I've never given you more than that. And so you're not even being asked to try to figure out some of the more difficult stuff. So it's so different. Do you know what I mean? Well, that too, but I mean, people can do the same thing in the quiz, but they don't. You know, I get people. I have a completely normal distribution of people getting hundreds on the quiz. You know what I mean? And so when that's not happening, I'm just like, how well am I preparing you for 303? That's my concern, is that this is just like too straightforward. But maybe it's not too. I just don't know. I've never done it this way. And so that's what I'm saying. And so it's the same with the final exam. I still am trying to feel out that and like how that should be structured. I felt like the midterm was too easy because I was worried about it on the midterm because it was early and because of all that other stuff. So I made it really straightforward. But that was way too straightforward. So anyway, we'll see. It's not like it's not like I'm concerned about this summer or anything like that. It's just you do have to move on and use all of this. And so that's what I just keep thinking about, is how well is that happening?
I mean, I can always keep every lab I've done as a resource as well.
But it's more
The critical thinking.
yes, it's the critical thinking. And I'm wondering if it's just not possible to do that. It's not enough time to do it in 6 weeks. Yeah, at least to make it even close to equivalent to what happens in the normal semester. I mean, I think everyone can use MATLAB, and that's also important, is to be able to use it as a tool. But the other part of this class is to be able to program, and that's the part that I'm not as satisfied with. Not with you guys. I'm not as satisfied with how the class gets you to be able to do that in the summer. More what courses? What?
You know, Advent? I forgot what it stands for. But at least in Washington, it's I guess like a higher level course where they teach you to think critically.
Oh, in college or high school?
High school. It's
Oh.
more of like a get ready for college thing.
Yeah, I mean, high school doesn't do that. That's the problem. People are coming in from high school and they're like, they have this expectation that learning is like, that the teacher gives them a bunch of stuff that they need to remember, and then the test is to just like regurgitate that information back. So it takes a while for people when they get to college to like transition to this other like thinking. It's not even really critical, it's like just thinking at all, you know?
I get you.
So,
I have to think a little bit of physics.
yeah, that's good that you think a little bit in physics.
Especially math is still pretty straightforward.
Yeah, math and something is regurgitating it. Especially in the summer. They barely show you anything.
In what? In calc?
Yeah.
I'm not gonna do everything.
Yeah, I mean, it's really hard. Like, so for Stanford, their summer session is the same as their regular session. Yeah, and a lot of schools are like that. It's not like 6 weeks is so fast. Like, it's so fast.
And then the last week everyone loses all their motivation.
Yeah, which happens in the regular semester too, but that's 1 week out of 15, and this is 1 week out of 6.
Yeah.
So, yeah. Okay, so we're going to do our last topic today, which is optimization. This is a topic that typically 303 starts with. It's like a really typical 303, just so you know, is like a numerical methods class. So the focus is more on like things like these last 4 topics, and the assumption is that you can program already, so they don't like go over how loops work or how functions work. Those are sort of things you've already developed. So for example, we're going to do an optimization code in this class. We're going to write an optimization code. And in 303, this might be kind of like the first one that you write, but you're going to do one that's just more sophisticated. I picked out the simplest optimization code that exists, basically. So optimization in general is sounds really dumb in a lot of ways, in that I think everyone knows what to optimize means. Mathematically, it means that you are searching for either a min or a max among a function or among a data set. And that's like how you can fundamentally describe optimization. But in engineering, we use it for so much more, to kind of like optimize design, optimize cost, or all these other things. And while it has more factors in it, its, foundation is still the same, which is to search for a min or a max. And so there's a bunch of different algorithms, techniques, and types of optimization. So let's say that you had some data or a function. There's 2 types. The first type that is kind of like the prereq to optimization is a root finder. So remember, roots are where a function crosses 0. And while this seems like like something that's not easily applied to any real system, it really is, because if you're ever trying to solve an equation, you can always just put all the terms on one side. That equation equals 0, and the root you're looking for is when that equation is satisfied. And so root finding is done all the time in engineering, and you'll see it a lot in your problem sets, that you'll get to a situation where you don't know how to solve an equation analytically. I'm sure it's happened before already, or happened in high school, where you don't know the analytical techniques to solve that equation, or you don't want to do it because it's messy. Then you root find, right? So it happens all the time. So these algorithms apply to that, as well as finding maxes and mins. They're really similar. And if you think about a min or a max algorithm, you're probably like, oh, you just take the lowest value, you just take the highest value. You're like, how is that complicated? So it's complicated because typically you're looking for all of the mins or all the max, so even the locals. And so thinking about how you can locate those is what you want to try to kind of, we're not going to be doing that, but think of going in that direction. So you've probably seen some of this in calculus. Well, you definitely have seen it, for sure. So a min or a max or an optimum is the point when the curve is flat. And that happens where the derivative is 0. And then you probably remember from calculus that you can tell whether it's a min or a max based off of the curvature, which is measured by the second derivative. And these are great methods of just being able to differentiate functions and things like that. But unfortunately, they're only useful when you are dealing with a function where you either know the derivative or you can take the derivative. So the way that we want to think about this is making it general for when you have just data, when you aren't able to analytically measure these things. And in general, with optimization, it gets a lot more complicated when you start thinking about constraining the problem. So let me explain that a little bit. When you get your textbook for 303, you'll see this, that there's all these different types of optimization. And each type is going to require a totally different dimensionality, a totally different algorithm and mindset. So let's just talk about something simple first, which is the difference between looking at something that varies in one dimension versus that varies in multiple. So let's say you're trying to find the optimum or the maximum of a 1D function. It's pretty straightforward to think of the algorithm because you can follow along your data and just stop when you have the biggest, right? And it's just one-dimensional. However, just think about, this is a contour plot. We did a couple of these in this class. So the middle is higher or lower. You could start like traveling along your data set trying to find your optimum, but what if you're going in the wrong direction, you know? Like what if you're just going in the X direction, or what if I took this path and I thought the maximum was right here? Or, you know, just thinking about it, it's just different, right? The way that you would search for that algorithm. Okay, the second thing that you can have is you can have a min or max. So that would be the type of optimum. So again, the algorithm is going to be different. You can't use the same algorithm for either or. So if you're using any intrinsic functions, which we do in this topic, there is a different one for the min and a different one for the max. The biggest thing that comes in with different types is the idea of having constraints. So an unconstrained optimization would be kind of like this one that I showed here, where you're just trying to locate the max, and it doesn't require that you hold anything to a certain value or constant or anything like that. So let's talk about what constrained optimization would be. So I'm going to give you a relationship. So let's say that you had an equation that told you that defined profit based off of the amount of regular gas and premium gas sold. And let's say you were trying to maximize that profit. However, there was some constraint on how much of that gas you could receive. So let's say that the supplier could only provide 77 of some units of the material with this ratio. So you're trying to maximize profit and you're trying to like optimize something, but there's specific constraints on the system. Like you could imagine for design this would happen all the time, that you were constrained by the amount of material that was available. You were constrained by the types of material that you could receive at one time. You know, options are endless. Does that make sense? So Excel is really, really good at constrained optimization. So most engineering textbooks that describe optimization for this constrained option use Excel. You can do a bunch of really fancy things in it. And MATLAB can do it too, but you know you have to program it all. Where there's already some features in Excel that allow you to do it a little bit easier. Okay, so for this lab and for this topic, we're going to be focusing on 1D, unconstrained optimization, the simplest one that you can do. So we're going to do the following algorithm. It's called the golden search algorithm. And the only reason I've shown this algorithm is because it's the easiest one to program. Optimization algorithms aren't really that complicated to write. That's why they're so often used as like the first numerical method that you program. And they get you to really start thinking about a lot of really important things with programming. So I'm going to show you today the algorithm for locating a maximum. And in your lab, you're going to think about how to adjust this for a minimum, because I'm really showing you the majority of the algorithm. So all you have to do is convert it to a minimum. And you can't just guess, you can't just switch signs, you have to actually think about it just the way that I'm explaining it. So the way that the golden search algorithm works is you need to start off the algorithm. It's a bracketing method, so it's kind of like thinking about how we did interpolation, the window interpolation algorithm in some ways. It's like combining that one and linear algebra. It's not combining those topics at all, but it's combining features from their algorithms. So the only way the golden search algorithm works is if you are able to tell the algorithm 2 points that bracket your maximum or your minimum. And we call those 2 points the lower and the upper points. And this is exactly how root finding methods work. There's root finding methods that are called bracketing methods that just give you a place to start and end and have you search in between using the algorithm. Or there's one step more sophisticated where you calculate derivatives, which can give you a direction to go. So you can just start with 1 point, and then the derivative will help you search for it, if that makes sense. And those are the two main types of algorithms. So this is a bracketing method. So it does not work if you don't give it the right XL, XU.
You can make those far apart as you want, right?
Yes, yeah, that's true. It will obviously take longer the further apart they are, but yeah.
It's as long as there's only one minimum or maximum within that range. Otherwise, it's kind of.
So this one, we're not writing a super sophisticated one. The one that we're writing is only able to find if there is one. If there's only one peak. If there's more than one peak.
I was looking into it last night to do that.
Mm-hmm.
They were saying that if you have an equation with more than one minimum or maximum, you have to pick your range to be bracketing only one of those.
Right.
Otherwise, it'll get thrown off.
Yes, it will get thrown off. This one, I would have to think about it a little bit of if it would find the wrong one or if it would never find one. I think it would find the wrong one. Yes, it would definitely find the wrong one. It wouldn't just always search because it's constantly removing parts of it. But yeah, this is the most simple. I should actually include this. I never have. It only works if there's only one optimum. So normally the quiz that I give for this topic is the next type, which is able to find more than one optimum. And you really need to be able to take derivatives to do that. So the first step for this algorithm is that you need to have a function or a set of data that depends on only one variable. I emphasize that because if you look at the lab, you're looking at drag, an equation of drag, and it does depend on multiple variables. I mean, it appears to, but you have to be very clear with which variable you're optimizing. So all the other ones have to be set. They're all given in the lab what they are, but you just have to make sure that those have values and you're telling it which one you want it to be able to optimize. Okay, then you need your bracketing points, obviously. So you need equal, yeah, it needs to be this. You need the XL and the XU that bracket the maximum or the optimum. Yeah, this is L for lower and U for upper. Yeah. It's actually pretty standard notation for bracketing methods is to use upper and lower. And you'll see why in a second. You start just like confusing yourself a lot of which two you're comparing, and just having good variables helps with that a little bit. Again, this isn't a very complicated algorithm at all, but you do have to think about the relationship between X, XL, and XU. Okay, so it's called the golden search algorithm because it uses the golden ratio. And technically, to write this algorithm correctly, it takes advantage of one of the features of the golden ratio, which I'll explain to you at the end. And I would say maybe like a handful of students incorporate the feature of the golden ratio into their algorithm because it helps speed up the algorithm. That's the reason you use it. But it isn't necessary to get it to converge. But the golden ratio, have you guys ever heard of it before? I didn't prepare my Donald Duck video. Yeah, I'll link it with the timestamp. It explains it a little bit, but it's just this like ratio that's seen a lot in nature because it continuously repeats itself, the ratio, and that's what I'll show at the end. But it's about 2/3 is what the ratio is, and so it's seen a lot in like art and stuff as just like a really nice, appealing ratio. And the reason it's appealing is because it repeats itself. I mean, we as humans, we don't think about that, but that's probably why we like it so much. So I'll show that at the end. So let's move forward, assuming that you know that there is a golden ratio, and it's about, just imagine it is about 60%. So you choose 2 interior points. And you choose them using the golden ratio. So the ratio is just like a percentage is the way you could think of it. So you need to convert the ratio into a distance that's relevant to the XU, XL distance of your bracket. So all you're going to do is take and find the difference between the 2 points, so how big your bracket is, by taking XU minus XL, and remember XU is by definition bigger than XL, so you can always do it that way. And then you multiply it by the golden ratio. So if this was like a distance of 1 apart, this would be about 0.6, and so if you moved in 0.6, you'd be about 2/3 in. Then your 2 interior points are just defined based off of that D. So you take your lower X and you just add D, and that's your first point. And then your second point is just your upper X, and it's minus D. So if I just draw that out, you can see that this is your XL, and this is your XU. and then D, or not D, this is your full distance, and then x1 here is going to be just the distance d away from xl, and x2 is going to be the distance d from the other side. So x1, x2 are like the actual x location, and d is the location away from the other bracket. And this is the part that I have to rewrite every single time. I can't think about which way the algorithm gets twisted without rethinking about this. Okay, then once you have those 2 points, so these are very easy to program. These are just 3 calculations, right? So you just, R is going to be defined. You're just typing this in verbatim, right? There's nothing special about the algorithm. Okay, next you have to evaluate the function value, or the y value, for those 2 new points. So the way that we are writing this algorithm assumes that you have a functional relationship between x and f. So what most people do is because this is how you have to use the intrinsic function, you guys had to use the intrinsic function for your pre-lab, right? So you know how you had to, I mean, if you figured it out, you had to use the function handle, the @ symbol. You can do that for this lab as well, or you can just write your function in a sub-function where the inputs are like w, v, and everything, and the output is f. So once you know x1 and x2, you'll just plug it into your other function and evaluate, and you'll get your function values. For those 2 new points. Okay. And then finally, you have to do a little bit of logic. So let's think about this. So this is the part that you'll have to adjust for them for your minimum. So I'm showing it for a maximum. So this is how I do it every time. I redraw a possible function so I can think about it. So this one, I'm going to assume that f2 is less than f1. So I'm going to draw the function so that that's true, so you could visually see what it is. But the idea is that you have x1 here, and you have x2 here, right? That's just how I wrote it up here. That's just how it always is. Now, if f2 function value is less than f1, that's the case we're looking at, which it is here. Do you guys see how it is that way? Then we want to be able to remove part of our bracket so that we can eventually get our bracket smaller and smaller. So it's pretty easy to tell that if you know that this one is less than this one, then you can remove everything before that. Again, only works if there's one bracket. But if you take that part of the bracket out, you should still have the maximum inside the bracket that you kept. Do you guys see that?
So the x1, okay, so the minimum or maximum is between the lower and upper, and then x2 and x1 are just guesses to kind of figure out exactly where that is.
Well, you just move in like 2/3 on each side, because yeah.
Oh yeah, every single time. Okay.
Yeah, so you're always going to be able to remove about 1/3 of your bracket, basically, based off of this. And if you do it enough times, you'll eventually have your XU and XL are like close enough to stop.
I didn't
So we're going to remove that part of the bracket. So you can either just say that you're removing from XL to X2, but in MATLAB, in MATLAB, all you're doing is you're resetting the lower bound equal to X2. And now your new bound is going to be from here to here. The second check is just the opposite. So again, I just like to draw it so that it's the opposite way, so that I have a max that's on the other side. So I still have my x2 and my x1, those will be set the same. But in this case, f1 is less than f2, so we can remove the other side of the bracket on this side. So we're going to remove from x1 to xu, which means that you can just set xu equal to x1 and just move your upper limit in a little bit. So you're going to have to resort this out for a minimum and think about how you adjust those. And then the final step of the algorithm is to repeat 3 through 5 until. So this is the same algorithm as we just did with Gauss-Seidel. You are going to do I call it an error checker algorithm, and you're just setting it in a while loop and running until I wrote the case. Sorry, I was just thinking about it. That would be upper minus lower. Upper is on that side. No. Yeah, this is always positive, so you don't actually ever have to do this. So that whole thing is going to go in a while loop, and the while loop is going to run until XU and XL are close enough. And again, just like with the other algorithm, the smaller you make this, the closer you're going to get to the actual maximum or actual minimum or actual root.
Is the top not absolute value?
No, because the upper is always bigger, so it doesn't need to be.
Would it matter if it was?
No, it wouldn't matter if it was. It should just always be positive. So let's talk about this a little bit. We got a while loop, we have a couple definitions, and then we just have an if statement. This doesn't have any loops inside because you're not repeating any calculation like you were with linear algebra. So the only loop is the while loop that repeats steps 3 through 5. But there's not like indexing or anything like that. Things are just getting constantly updated and replaced. So let's just talk about why you use the golden ratio. Okay, so let's draw out the lower and upper bounds. And just going to show you a few lengths. So the distance between the original bracketing pair, I'm going to call L0. Now, I already showed you that the max is on the left side by the function that I drew. So I'm just going to show you dividing it up into the 60% that we're using for the golden ratio, which would be this left side here. So let's call this L1 and this L2. Oh, I can't just explain this. I have to explain more after this. Shoot, I thought I could just explain this. So with the first iteration, do you guys see that this will be removed? This section, the L2 section, will be removed. And you'll have the L1 section. So now this is going to be your new bracket. It'll be your new XU, yeah. So then what happens is maybe this will make sense. You're going to break it up again, right? And it's going to be another 60%. And because of the golden ratio, these are actually the same. This L2 and this L2. Yeah. That's what the golden ratio is basically, is that that percentage keeps breaking down and it reuses the smaller side because it becomes the bigger side of the other side. And so what that means is you've already evaluated this function, the function value at this location, because when you broke the bracket up here and you did L2 from here and L2 from here, you already evaluated it. So you don't have to reevaluate both function values each time you do the iteration. So you only have to evaluate one of the function values. The other one is calculated from the previous iteration. And so you can easily see that by just printing your function values out each iteration and just seeing that you'll always get a repeat one from the last one. And so you can even just fix your algorithm to not call your function evaluation just by doing that, basically. Maybe it would have helped to show this. But that's the basic benefit of the golden search algorithm, is it reuses one of the function evaluations. And obviously we're not doing a problem that is going to show us any speed up or we're going to get any benefit from that. And honestly, the algorithms that are actually used in these types of optimization are so much better than this that doesn't really matter anymore. But it's a kind of like a cute thing, you know what I mean? And like it's a really common like programming exercise to be able to incorporate that. So it's up to you how far you want to take that, if you want to incorporate that repeat function evaluation. So, do you guys have any questions? Yeah, and I could show how to do the intrinsic function or do function handles. I should show that, sorry. I know you're looking forward to being done. But I should show how function handle works. I think that would be helpful. I usually show this in lab. So this is used a lot in 303 function handles because 303 uses more intrinsic functions. Like you do a bunch of, you still write a lot of your own, but you also use a lot of the differential equation intrinsic functions, and they all require function handles. They're not complicated to understand at all, but if you've never seen one before, you have to take a few minutes to understand it. So let's just give you an example. So let's say that you had a function, some function that you wanted to be able to define the f value for different variables on the right-hand side here. So I just have 4x plus a. X and a will come in as inputs, and f will go out as an output. Pretty much all of these intrinsic functions, including fmin search, require that you somehow give it this information. So this is how you write it as a function. Function handles have been developed to make this shorter. So what you do is the shorthand is just that you define the output. What's it called? I think you just do F. I should try it. Okay, so let me show you this really quick. So if I run this, I'm just calling define F. Did I call something else? I'm calling define F. I'm plugging in 1 for X, 2 for A, and I'm saving the output to F1. You guys see that? How that all gets called? Okay, so an alternative way to do that is to use a function handle. So the function handle requires that you give the inputs behind an @ symbol, and then you write out, because these are always pretty much just one line in the function of just defining an equation. So that equation gets defined behind the @ symbol. So this is telling you what your inputs are. This is telling you what your output is, and then this is your equation. I'm like not 100% sure that I did this right. And so the syntax is just different, so it's just like a quicker way to write this. This takes 3 lines and requires that you write function and all of that, where this is saying just like here's 2 inputs, here's the function, and I think the biggest difference is that the output and the function name become the same. So here to call this, I had to call define F, and then I called define F, and then I sent it to an output, where here the function and the output have the same name. So function handles basically always have one output, and that output becomes the function name. So you have to be able to use this in your lab to call fmin search. And it's a little bit easier in the pre-lab than it is in the lab because the lab has multiple inputs. And so you have to be able to tell fmin search which one of your variables in your function handle is the one that you're trying to optimize. It's like which one are you trying to find the minimum for, which is velocity. And so this would be how to write as a function handle. Does that make sense how function handles work? So the purpose of them is so that functions that need to be able to reevaluate other functions, like an optimization code needs to be able to go find function values, right? Like we just did it. There's no way to be able to locate a max or a min without being able to recheck function values. So you need to send in a function into the fmin search. And so the only way to do it is to use a function handle or write it as a regular function and then send it in with the @ symbol. So we can talk about it a little bit more in lab, but that should give you a good starting place to think about it. Okay.